Okay, the experiment I'm talking about is I took a couple of magnets, and one was this shape, just like this little, cylindrical magnet. And what I did was I ground the middle out, okay? If you see that, I ground it down. It's getting beat up from experiments. So I took some material out of the middle here. And as I took material out, and up to this point, what happens is, if you notice, that's the north. And as you come along, let me get my button down, it turns to a south, okay? It's like I've made two magnets. Then it dies, and then it goes to a north, which is actually the south. So basically, it's like two magnets, but they're conjoined twins in the middle. So in here, it's like that video I showed where you have conjoined twins, but they're looking at the outside of the magnets at the same time. You see what I'm saying? This one's looking at a south towards the north, and this one's looking at a north towards the south. So I basically have two magnets, but it's a solid piece, it's all one piece. The middle is still got a dead spot in there, and so does the ends. Dead spot south, north, south, but it's more like the sphere was, The lights change much quicker than it did with this one, with that dead spot so long in the middle, see? Anyway, beyond that, the original magnets all have basically the same gauss. If you watch the meter, positive 0.50, pretty well 0.50, and let me do this positive. This one, 0.49, 0.50. Even with that material missing, it keeps the same gauss, okay? Let me show you that. North on this, the north on the changed magnet is 1.55. The other one was 1.50. This one is 1.55. It maintains the gauss, even though it's missing mass in the middle. That's kind of interesting in itself. But if you notice this, when I put this north, which is the other side of this south, because I've got two magnets now, basically, that north over is still 1.52, 53. It's almost what this north is a 1.55. It's just shy of it. Just shy, 2 points. It went to 1.54 there, I saw. But, it's missing more than about half the material all the way around, symmetrically around it. And the south is the same way, 1.49, and this south will show 1.434445, and it's because I had my length a little off here probably, and I may not be as deep on the south side, but 1.44, I saw 4244, and this was 1.49. So what gets here is what I'll show you with the electric current in a moment is it's pulling in the ends like I tried to show you with the sphere and this. But when I ground this out in the middle and basically made two magnets, but they're still connected, the electric arc's going to pull to each one of these poles. They're not completely ended poles, but there is a pole there, as you can see. That shows a positive, and it's easier to do it with this. That'll show a south, even though it's the north end of the magnet. So I basically have two magnets. And that'll show a north on that end of the south. I hope you see that. And I'm going to show you something that's real prolific and important about what this represents. So anyway, that's this one. Now I'm going to move on to show you another magnet I did. It's a little more interesting, and we'll do that. Okay, on this one, it was a sphere. My sphere magnets I mess with all the time. That's what it was when I began. Just a round 1-inch neodymium N42. So what I did, I ground the middle out all the way around it. And I'm going to show you what this represents here in the next section after the electric current. And the funny thing here, that shows 1.50 on the south and 1.55 on the north, basically what the other N42 did. This will show 1.54950 on the south and 1.55 on the north, even though it's missing all that mass, okay? And it does show, this one's hard to do with the pole finder. That is the south. If you come around, it'll blip to a north, if I can get my pole finder in there. South out here, and it usually blips to a north. There it is, the north there, south there. And this side will be a south there and a north there. See that? South there, north out here. Does the same thing the other one does. They are trying to pull together because you got a south and a north as far as rotation, but since they're held apart because of the piece in the middle, this one's running in that way and this one's running in that way, you know, spherically, rotation spherically, but they're curved. You see what I mean? It's curving in that way as this one's curving in the other way. So they're kind of back to back, even though they want to pull together because of the rotation, but they're back to back because that piece in the middle keeps them separated. So I showed you, you know, and on the inside, it shows a north. Now, this is the south one, right? It's blue. You can see that. I can use the pole finder if you want. The blue side will show positive here, 1.49, 1.50. On the inside, it'll show a north, 1.55. The same thing it does here, 1.55. I maintained the Gauss in here on the north as I do out here on the north. And I think the south is a little different. 1.49 on the south. This south will show a 1.4849, same. So if you see what I'm saying, the south here and the south there show the same Gauss. The north here and the north there show the same Gauss. And like I said, they're trying to pull together, but they can't because of that stem in between them. So this one's curving in that way, that one's curving in that way, and they can't come together to actually form, you know, two magnets laying together like it normally would, like these two. It can't come together with the full rotation. So that's why it shows that dual poles, you know, just like when you stack the magnets, and even on the program you showed, where there's a little gap between these, that's a major gap. And after the electric current, I'm going to show you what that really means. But for right now, hoping this will show up. If I put this magnetic paper, it's kind of got some lines. I tried to clear it. You can see the two poles in the middle there. See the two little ones in the middle? Look how big the outside ones are. Can you see them? Let's get it up like this. Get the crease out. The two outside ones are real big. The two inside are much smaller, if you see that. The two inside here are smaller, but you have a north and a south. And look at that line between them is just like a magnet, you know, shows on a sphere, but this is that shape with that little bitty piece in the middle. And this is going to, you know, turn into something else, especially if you turn it different ways. You'll see it like that more. I've turned it up now, and you can see it a little differently. The two in the middle and then the two bulbs on the outside. I mean, the two inside ones don't show as much, but they have the same Gauss. They don't show as much here as the big ones. See how big these are out here? But the inside ones are much smaller. These are dominating, but it's all rotating in the same direction. That's that one. And I can show you the other one. Has a similar, if you see that one, that's this cylinder magnet. You can see the two in the middle are close to each other, the outside edge. Outside ones kind of reach out farther, but the two middle ones are constricted. And that's very important. And I'll show you why that's important after I show you the electric current part, how it works with this one and the sphere when it's mangled. So that's that part. We'll move on to electric current, and I'm going to move on to show you what this represents and how I see it. We'll move on. Okay, now we'll use the electric current to show you that, you know, like I showed you before, it's got a north and a south, like it was before I ground it. But on this side of the north, get my pole finder, there's a south, and on this side of the south, there's a north. So it's coming in here on a north pole and a south pole that way into that lobe. And then this lobe is coming in this way on the north pole and then the normal south pole. I want to show you with the current what that does. It shows it's doing that. It'll pull it up or down. It won't stay in the middle. Pulls to the north there, or the south there. And it depends on which way I've got it or how smoothly it does it. I mean, it pulls it up. So that will pull it to whichever input there, see? It's going to that intermediate inputs, north or south. It'll pull it either way because the rotation's much smaller there. And they're fighting each other much closer together. One's pushing it down, the other one's pushing it up, but it will get one on top, one on the bottom, and get caught in the rotation to make its way across. And it's going through the neodymium stuff more in the middle there, because right between those two poles, you know, north and south, you've got that another dead spot. But anyway, that's what that does. It does pull it to the other inputs there that I've created, a south and a north. All right, we'll move on to that other shaped one. Okay, here's the other one. That's the sphere that I've mangled. And I'll show you what it does. This does a little different because it's so close. But it still pulls it to one or the other. Inside the missing area, the void area, still pulls either the south pole or the north pole. It pulls down on that side. Out here, well, I can't do it there, but it's connected. It pulls away from the pole, and then here, it just pulls the same way it does on top. It's pulling from each side, inward, or outward. Inward here, outward there. The north does the same thing. I can flip it. It's starting to get hot. But the north will do the same thing from over here and there, or it pulls up underneath. I should probably do this one this way. You see that goes there or up there. It won't go to the middle. It pulls to one or the other. It's being pulled one way or the other. And it will cross across them in the rotation, but it does the same thing if with a regular sphere turns that way. But I can't get into that way or I'll get my fingers. Okay, if you remember my earlier description of a quasar, I showed you the spinning ball with the water, and I thought that the magnetic field went through. It was my old theory, and I thought it was kind of like this. You know, had dual magnetic, like coming in from here for the middle one and then going out both ends. I understand now that's not what's going on, and it still can turn into binary stars, but the difference is this is not what's going on. This is a quasar. They have to be big. This is also what you see the comets. And I'm going to show some pictures. I'll, put them back to back, the comets and the quasar. But the reason I say that it's a quasar is because of that doubled in the middle, in between. They're kind of coming in towards each other on each opposing direction in the same rotation, but since there's something in the middle where they can't pull together, they have to separate more so than they would if it was two separate magnets. You see what I mean? When it's two separate magnets of the same basic, connection piece in the middle, you have balanced equality, pretty much. You get a little bit of ISO lines showing here. Here, you get major ISO lines because you basically have two separate magnets like these, but they're separated where they can't pull together. So, you know, they're both feeding in, rotating, and they want to pull together, but they can't because there's a centerpiece. I think that's how quasars work, and I think that's why comets display what they do. That's why they have such eccentric orbits. They're big magnets, but they're not, you know, like a quasar. They don't have a lot of gas and stuff around them. They just have basically ferrite stuff and metallic stuff stuck to them, and maybe some ice in there or what have you. But the majority of it is just a magnet like this, shaped like this. And hopefully maybe I can do this, do a picture of it, and then put it with a picture of a comet and a quasar. Move some of this out of the way. Get a good picture of it. North up. My mangled magnet, and on the right is, I don't know if that's Comet P67 or Halley's, but here they are. These are comets. They're different. They're not the same ones. There's several of them. I'll show you some more pictures in a minute. But I believe that's why they're shaped like that, is they're magnets. And I believe it's still Birkeland currents that cause them to shape like that and become magnetized. That's why they have those fuzzy, when the rays of the sun and the plasma from the sun hits them, it's always got a fuzzy thing. And here's the quasars. I think that's why they blast out like that. That's that piece in the middle. And all these quasars, they have that. It's kind of like, what's his name? You know who I'm talking about. David Laporte. You know, what he shows with an array of magnets. But I think the Birkeland current, when it came in, there's two different ways it could have hit the quasars and the comets and some meteorites to give them that cut look. It could have been this way, like the magnet sitting there in the middle of them twisting Birkeland currents. They might have looped in from each side and just kind of burnt it like similar to that. That's a possibility. That's why it's magnetized, you know, in one direction. That's a possibility. Another possibility is if you turn it this way and the Birkeland current comes in and hits it, and let me get a picture here, hits it like that, it could wrap around and still magnetize it, but I don't know how the magnetization would happen. That would be them going past it like that as that thing spins in between those rolls of Birkeland currents. So anyway, here's some more of them comets. I think that's how they got cut like that. That Birkeland current just tore them apart like that. And I think that's how quasars work too. It's the same similar thing, but they're huge.